Hi everyone, this is Kailash Gogineni. I'm from the George Washington University. I'm a fourth year PhD student. I'm working with my co-advisors, Dr. Pangway and Tian Lang. And I acknowledge my advisor, Dr. Guru Venkatramani, for supporting me in this work. So let's get started. So today's topic is the scalability bottlenecks in the multi-agent reinforcement learning systems. So the talk outline goes like the first. I'll be giving a brief recap on the reinforcement learning systems and some of the foundations and the background information on reinforcement learning. And of course, as many of you would know, nowadays like multi-agent systems have become an important research field, and especially in the autonomous mobility and the traffic congestion control systems. So I'll also be introducing some of the basic formalizations and the algorithms which we used as an evaluation to perform the workload characterization and analyze the scalability and also the computational bottlenecks from a systems perspective. And then I'll be also discussing the preliminary evaluation with some of the observations we have identified. And I'm open to discussions in order to propose some of the solutions and take some feedback. And then finally, I just conclude the talk. So yeah. So the preliminary goes like this, like like in a basic reinforcement learning system, as you all know, we just have like a single agent, and the main elements of an reinforcement learning system are an agent and an observation and an action and also an environment. So at each time step t, right, the agent receives an observation OT, and then it kind of executes that observation OT on an environment, right, to get an it basically uses mapping function to map the observation to a specific action. So that action might be like a deterministic action or a stochastic action, which also includes like the action will be in the form of probability distributions. So the higher probability distribution will that will lead to that particular action being executed on the environment. So the environment after the action, after the agent executes an action, AT, then the environment emits the observation OT plus 1, which is the next state, and also it emits the scalar reward, which is RT. So this RT is basically the goal, like in any game or in any multiplayer games, right? The goal of the system is to of the agent is to achieve the highest reward, and then this T increments at every environment step, and then this process goes on until the system until the agent is converged or until it achieves like a highest reward. So this is like a simple example, as many of you know, like of Atari games. Like this is the first and the famous example in reinforcement learning system. So here, our environment is basically an Atari game, and we have four elements. The first one is the objective, which where we need to complete the game with the highest score, and the state here is the raw pixel inputs of the game state, and then the actions will be the agent going left, right, up and down in different directions, and the reward will be just an increase or decrease at each time step. So that is how a real world application of a Atari game works. Okay. So the main elements of the RL systems are the first one is the policy. So as I told, we need some mapping function to map an observation to an action and then execute that action on the environment. So that mapping function is called a policy. So this helps the agent, it maps the state, to an action, and then, as I told, this policy might be like a deterministic policy, and also a stochastic policy. So in this work, we only considered the deterministic policies. It is shown in the below equation, like we use a function pi, which takes a observation or state space, and then it gets the action. So the action will be just a deterministic one, choose in different directions from the before example, and then the reward. So what is the goal of the game, like any game, like or a multiplayer game, right? So we kind of need to maximize our total cumulative reward, right? So this is a sense of how good our state or how bad our state is. So what gives us the reward, right? So that's the value function. So the value function is it's a scalar which is specifying what is good in the long run. So this is like like a simple dynamic programming. It kind of moves iteratively. So we'll be discussing more details on the value function in the coming slides. So value function is a prediction of the cumulative future reward. So it is used to evaluate the goodness or the badness of a given state. So the equation describes that the value function at a given policy pi is it is an expected value for a given policy which takes the reward and it also applies like a discount factor to quantify the importance of the future reward values. Okay, so let's come to the multi-agent reinforcement learning systems. Okay, so first and foremost, so as you all know, so what's the main difference between a reinforcement learning system and a multi-agent reinforcement learning system? The first and foremost difference is that in a reinforcement learning system, we have one agent, and we take one observation, and then we execute an action on the environment, and then we receive a reward, and then it's like a trial and error using a feedback loop, right? We kind of update our policy. But here in a multi-agent reinforcement learning system, it's traditionally the mechanism is same, but the transition to the next state and also the reward are both are the functions of joint actions of all the agents in the environment. So the only difference between a multi-agent reinforcement learning and a reinforcement learning system is that in reinforcement learning also you can execute multiple agents working in parallel, but they don't share any environment. So they kind of independently run, and then they kind of later after all the parameters updation, they kind of synchronize. But here all the agents run in a shared environment. That means that each agent's actions influences the environment and also environment dynamically, and also the rewards of all other agents. So that's why in reinforcement learnings the scalability and the computational bottlenecks might be a critical thing.
Is there less stability with multi-agent systems? I could imagine compared to a single agent that it just constantly is maybe a sort of random walk, and the behavior of all of them is constantly changing as opposed to converging to some stable sort of behavior.
You're right, because in multi-agent systems, like you normally need to cooperate and communicate. So that communication and the collaboration between the agents might introduce a lot of complexity on the environment. Like whereas running them parallelly doesn't have any problem. So that's.
So if multiple agents are taking action, then the state change that an agent observes is the result of the change caused by multiple agents, or only by its own action?
That's a very good question. Normally in multi-agent reinforcement learning, in this work there are different types of categories, but in this work, I'll also be discussing that in the future slides. We only consider actor-critic methods, where I describe actor corresponds to the policy, and then a critic corresponds to the value function. So here what happens is the policy is individual to each agent. So each agent executes an action on the environment, and the value function, instead of taking a single agent's state action pair, we take all the agents' observations and actions. So that's how the other agent gets to know what the other agents in the unique agents are doing in the environment. So for example, I'll also be discussing one of the applications with a real world example. Maybe that will be clear. Okay, so many real world scenarios have more than one agent. The first one is the autonomous systems, and the first one is the self-driving cars and the traffic congestion reduction. So for example, in the self-driving cars, so assume a traffic congestion reduction scenario, right? You might have the automated vehicles, the human drivers, and you have the traffic signals and the pedestrians, right? So all these cannot be modeled as a single agent scenario, right? So for example, you need to somehow learn that if a car has a crash, right? So it needs to be rewarded using a large negative reward. So in that way, in the next loop, it kind of avoids a lot of car crashes, right? So even one of the real world application is the CarCraft, which is created by Waymo. So they kind of created like a CarCraft simulator that that imitates the human behavior, which is installed on the different automated agents, and then the automated agents in that case are the autonomous vehicles which are in the real world. So then the pedestrians are different agents. So they need to have a coordination, like they need to share some 2-byte message or whatever to to kind of communicate that okay, when the pedestrians are kind of walking on the road, we need to have a traffic light signal and so on like that. And considering the disaster response, so for example, in the aftermath of a disaster, right, the responders might need to know what is the urgency of different types of patients. So some of the patients might need to, they need to go into the intensive care unit, and they require immediate ambulance or emergency support. But whereas some of the patients might not be that serious. So for all these things, like you might not even have the complete observations, and you might even be having the partial information, which is used to communicate with the responders. So in that way, considering the responders as multiple agents, right? The corresponding agents will be the the patients or the contingency unit, the intensive care unit. So you kind of need to communicate and cooperate with each other to effectively provide the service in the disaster response. And other applications include the cyber deception, where you kind of create like a deceptive engine where instead of just confusing the attacker, right? One agent can monitor the intent of the attacker, and then other agent can try to confuse the attacker and engage him in order to waste his resources. So there are some of the terms we need to know, like before we move further. The first one is the value iteration. So the value iteration is basically, it's a part of the value function. So in multi-agent reinforcement learning, we'll be having like 4 networks. The first one includes the actor network, and followed by the value function. So that gives the value of that gives the value to the actor, saying which if the state is good, if the executed state is good or bad. And in concurrent, periodically we also run the target actor and target critic networks to update the parameters, to stay and also to stabilize the training of this whole multi-agent reinforcement learning system. So the main goal of this Bellman equation, it is decomposed into 2 parts. First one is the immediate rewards, and the second part is basically we use a discount factor to quantify the the discounted future reward values. So the main goal of this value function is to we kind of need to on the downside, on the down line of the algorithm, we kind of need to converge to the target value and the actual value must be same, in order to say that the algorithm has converged. So this function is helpful to decide decide and analyze and give a feedback to the actor, give a critic to the actor, saying that if the executed action on a given state is good or bad. So in this article, like we have performed a workload characterization on the 3 most famous algorithms. The first one is a multi-agent deep deterministic policy gradient, and the remaining 2 are just the offsprings or some of the variants of MADD-PG, and the second one is the MATD3, and the third one is a MASAC, which is a soft actor critic architecture. So before going to the algorithms, so the main the important thing is we as we discussed the actor critic method. So as I already mentioned, the policy is referred to as an actor, and the value function is a critic. So actor critic algorithms are they are the derivatives of the policy function, and they kind of alternate between the policy evaluation, and then first we compute the value function for a policy, and then we kind of improve the policy, and so basically a value function, it improves it basically helps the agent to find the best optimal policy. So in large scale reinforcement learning problems, it is kind of typically impractical to run either of these steps, to convergence, because as I told, the value function here is not just a function of one agent, but it's a function of all the agents, which are available in the environment. So we consider the centralized critic and the decentralized actor approach. So all the algorithms, they are kind of built on the same architecture. The idea of this CTDE methods are they kind of reduce the non-stationarity, and they do all the credit assignment issues using a central critic. So the central critic, the meaning of central critic is that since each critic, of course each agent has its own policy and critic, but here for each agent, the critic, the central critic with which it is concerned also has the observations and actions of all other agents. So that helps to influence the environment dynamically and change the rewards of other agents. So for example, if you're this is also applied to both the cooperative and competitive games. For example, if you're running on a cooperative game, right? There are many scenarios in real world that you kind of need to collaborate with multiple agents, and then you kind of need to compete against different agents. So in that way, when the cooperation is needed, there needs to be the communication between the agents. Communication in the sense that might be that sharing of their observations and sharing of their actions, and competitive in the sense that both the agents, they don't share their observations and actions. Instead, they work like single agent algorithms. So here in the actor critic, centralized critic and decentralized actor approaches. So the first actor one indicates that agent one executes an action one, and then agent one executes an action one using an observation O1, and then it receives a reward and the next state, which is S and R. And then similarly, it's like as this is a multi-agent reinforcement learning system, we also have an actor two, which is an agent two. So it executes an action two based on O2, and then based on the next state and also the action of actor one, we kind of calculate the discounted future values, which are also called as the Q values. So in simple words, the mapping, there are two mapping functions. So the first mapping function is the actor network, which is a simple multi-layer perceptron for these types for some environments, and it outputs an action based on the observation. Whereas the critic network, it takes the state action of all other state action pairs of all other agents, and it just outputs the Q values or the future discounted values for that particular agent. So the differences between the three algorithms, MADDPG is I think to my knowledge that's one of the famous and the one of the early algorithms in multi-agent systems. And MATD3, the only difference between MATD3 and MADDPG is that they use a twin delayed critics to tackle the overestimation bias problem. So because of the approximation made by the MLP network, what happens is the Q values, which are outputted by the critic network, are being given overestimation. So in order to reduce that, what MATD3 does is it simply uses twin delayed critics. That means instead of one critic, we'll be using two critics in the same process. So the final algorithm is the MASAC, which is a multi-agent version of soft actor critic algorithm. So MASAC obtains higher rewards and also the improved convergence in both competitive and cooperative environments. So MASAC, like the only difference is that it kind of assigns equal probability to nearly optimal actions, because in MADDPG it suffers from a bottleneck where it kind of repeatedly selects the same actions, right? Selects the same actions. So in order to avoid that, MASAC is one of the variant which is introduced to assign different actions. So coming to the algorithm, so there are three parts in all the three algorithms. So the main thing is the policy. When the policy is in action, the policy in the sense it's an actor network. So all the agents, they try to execute their observations, and then they try to get a list of actions, and then they try to execute all the list of actions on on an environment. So the critic network does not start the parameters the back propagation at that pace. So what it does is we kind of need a buffer or an experience replay buffer to store the information that we explode until then, and then later we kind of need to use the experiences what we have executed and what we have observed on the environment, and then that information is used to correct the actor. So the critic uses the observations which are stored by the actor, and then the actor network and the critic network both are updated. So the first equation, which is the experience replay transition, so is the first one where each agent. So here X indicates that it's an observation of agent 1, and X dash indicates the observation of agent next observation, which is obtained from the environment when we execute X on the mapping function, and A1 is basically the action of agent 1, and so on. You store all the agents' actions, and then R1 to Rn is basically the reward of all the agents. So here, in terms of an algorithm's perspective, so this is stored as a simple array, but in terms of a systems, from a systems perspective, this we kind of have like the replay buffers are directly proportional to the number of agents. That means if you have 200 agents, working in a really big scenario, that we'll be using 200 experience replay buffers. So that indicates that each of the transitions, they may be stored at different memory locations. So coming to the centralized critic, so we use the experiences. So for example, the policy is kind of warms up for some time. It kind of explores the environment, and it kind of receives some reward, and it stores all the transitions as a tuple. So what in the centralized critic, what we try to do is, so this E of EXAR X dash, it's like a transition which is sampled. So so that sampling size is the milliband size we use. So normally in our studies we used 1024, and the buffer size is actually 1 million. So that means the centralized critic at each time step needs to sample the 1024 number of transitions, like the vectors, from a buffer size of 1 million, which is actually huge, and it also it does a random sampling. So that includes that grabbing the transitions from different memory locations, which is a complex process when multiple agents are involved, because the centralized critic needs to extract the data from all the buffers for a single agent I, and it needs to continue the same when they're not for all the agents. So here the process of collecting the data is a function of other agents. So the next equation Y is basically that here we in order to update the critic, we simply use a mean square error loss, and then we calculate the Y, which is a target value. So whenever the first term, which is a QI, which is the Q value for a given policy pi, which includes the observations and actions of all other agents, and then the Y is basically the immediate rewards, and it is decomposed into two parts. The first one is the reward plus the discount factor into the target Q network. So as I told, we have 4 networks. The QI pi is a critic network, whereas the QI pi dash, which is a target critic network. So this helps to increase the training stability and also to update the critic network, because finally the critic network is the one, the values obtained from the QI pi are needed to update the actor network and use it as a feedback to improve the convergence. So the decentralized actors, they are trained via the policy gradient. So the first thing is the pi I, which is indicates that's the actor portion. So where we use a policy for each agent, and then we obtain an action for an agent I, and from an observation I. So the next part is the QI pi, which we simply use it from the critic part. If you see from that the second equation. So what we try to do is we need to, when we are updating the actor network, we need to take the gradient of the critic parameters in order to update the actor network. So that's how the critic actually gives a gives his views or opinions on how good or bad that that actor state or the action space is. Okay, sure. Okay. So all our experiments are basically conducted on the Ampere architecture, which is a high-end GPU, and the environment we have used is the predator-prey task, where n cooperative agents work to block the way of m prey agents. So here the prey is basically the environment control. So to quickly go over the functions we have used, so we have divided the algorithm into multiple parts. The first one is action selection, where we use a policy function, and update all trainers, which involves the mini batch sampling, which by sampling 1024 transitions, and also the target queue calculation, which I already described, and the final one is the upgrade. Q loss and P loss is basically updating the critic and actor networks, and the environment interactions is basically when the agent interacts with the environment. So I'll just, due to the time shortage, I'll just show the results for one algorithm. So we have conducted the results for from 3 to 48 agents. So the 48 agents literally took us 10 days to train the algorithm. So the left-hand side chart indicates the whole algorithm training. Here we have divided this into 3 parts, where you can clearly see that as the number of agents increases, update all trainers kind of dominates the training time. So it occupies 90%, 87% when the number of agents increases to 48, and whereas action selection kind of reduces. So that's why we delve deeper into the update all trainers. So the main functions in the update all trainers are the mini batch sampling phase, the target queue calculation, and the critic update and the actor update. So you can clearly see that the mini batch sampling is the highest time consuming phase. So the reason is that it might have lot of memory access patterns, where each agent needs to grab the data from different memory locations, and also between the iterations, since it's a random sampling, there is a less cache reuse, which might also result in a lot of cache misses. I'll skip these slides. Okay. So this is the training time growth of update all trainers. So you can clearly see that normally when the agents increase linearly, but the growth rate also should be at least linear. But here all the phases inside the update all trainers, they kind of grow almost 3.5 to 4 times, which indicates that the data collection and also accessing the data from the random memory locations is the primary bottleneck. Okay, so these are some of the challenges we have observed. So I'll just to conclude, as the number of agents increases, I've already discussed this. The update all trainers grow super linearly. So, and the main problem is the curse of, it's a dimensionality. So when the number of agents increases, the vector space of the observation and action space increases. And the third one is the random memory access patterns in the sampling phase. So maybe clustering or doing a macro batching helps to reduce these problems. And the target queue calculation, where we kind of need to do n into n minus 1 memory lookups, because each agent has to do the memory lookups of all other agents. And then the back propagation is that as the number of agents increases, the trainable parameters increase, because the observation space and the action space increases. And n critic and actor networks are built, which incurs extra time to update all the weights of each agent in a sequential manner. Yeah. In summary, so we have proposed the applications and foundations of. We have discussed the applications and foundations of reinforcement learning, and then we have done some functional description and partition some of the important functions in reinforcement learning, and then we delve deeper to perform a workload characterization on all the functions, and then finally we identified update all trainers is the most time-consuming phase when the number of agents increases, especially in some large-scale systems. So, and we also observed that there is a clear superlinear growth, and also there's a huge computation and also scalability growth problem inside the update all trainer space, which is because of the mini batch sampling and the target queue calculation and the back propagation of both the actor and critic networks. That's it. Thank you. Any questions?
Thank you.
How did you reach the random multi-axis pattern conclusion? Did you do some characterize?
Yes, sorry about that, I had to go a little fast, but I'll push over that. So here, so we try to calculate the growth rate of the mini-batch sampling. So mini-batch sampling is the place where we try to extract the data from different locations. So what we try to do is we try to calculate the growth rate. For example, when 3 agents take X seconds, so we try to, see like what is the, what time.
Getting the random memory access pattern, did you use some profiler or something?
Yes, we have calculated the number of cache misses. So using the perf tool, yeah, and we use some of the profilers to calculate the cache misses. And then what happens is in between the iterations, since they are random indices, there is no cache reuse. So all the data which are abstracted are different. So that gives rise to a lot of cache misses.
I'll ask one question too.
Sure.
So generally you have a centralized critic except for MATD3 where you've got the 2 critics.
Right.
That having a single centralized critic seems like a significant scalability bottleneck. Why not have multiple decentralized critics?
So-
More than 2.
Okay, so the difference between a centralized and a decentralized thing is that centralized takes the information of all other regions. So that's if you make the critic also a decentralized thing, then it's a simple single agent algorithm. So because in a real world scenario, you need the information of other agents, right, in order to adapt yourself, and the reward depends on other agents. That particular agent.
But critic is also a neural network, right?
Right.
So you can partition it and you can do like some sharding of that so that different component, like a model partitioning of that.
That's a good.
Or model
Or
partitioning.
federated learning like.
Right. So that's a good question. So in the algorithms we use, we have 4 networks. Actually, we have it's an actor, critic, and a target actor and target critic. But the network we used in the algorithm is one and the same. So it's just a 3-layer multi-layer perceptron. So what happens is it's just the input we give to the network changes. So that's the difference. You might have, like, as you said, different networks, but that also might induce more complexity, because in the scenario we have considered, so it's just a vector space, right? The environment we have used is relatively a smaller environment, but still when we try to train it with 48 agents, update all things.
So the other thing is that these agents here, why it is the training time increases with the number of agents, because why you're doing them sequentially, these agents can themselves be different processes and you can do multi-processing there.
So that's a good question. But in order to do the centralized critic, each agent needs to they need to execute on the same environment. You can't have independent environments. So only when you execute agent one's action, of course you can do the action selection as some multi-threading. So where action selection is just a portion where you kind of map an observation to an action.
Right.
So that can be done in parallel. But the back propagation, as I said, the Q loss and the P loss, that can also be in a parallelizable way.
Yeah.
But the mini batch sampling is you need to warm up for some time. Like the algorithm needs to warm up in order to collect the data. So this can't be done in parallel because it needs the data of all other agents, and this process has to be executed sequentially in order to in order for the environment to, because on the environment we execute these actions as a list of actions, and these are executed in a sequence, right? So only when agent 1's action is executed, then we get to see the agent 2's action. So that's how this model works. Yeah. Yeah, as you said, the Q loss and P loss, they can be parallel on a
Okay, so I think in the interest of time, there's a breakdown. Not sure what exactly is out there, but thank you very much. Very interesting talk. Nice work.